Here is a habit so familiar you never think about it. To undo 2 times x equals 6, you multiply by 1 half, and out drops x equals 3. 1 half is the number that turns 2 back into 1. 1 half is the inverse of 2. So a fair question is this: can we undo a matrix the same way? Can we find a matrix that reverses whatever another matrix did? Let's watch it happen. On the plane, here is a unit square with 2 arrows for its edges, gold going right, rows going up. Now apply a matrix A. It shears and stretches everything. The square tilts into a slanted parallelogram, and the arrows swing to new places. Space has been transformed. Here is the magic. Apply the inverse of A, and every point retraces its path exactly. The parallelogram folds back into the original square. The arrows return home. A inverse perfectly undoes A. That is the whole idea. To say that precisely, we need the do-nothing matrix, the identity, written I. Once down the diagonal, zeros everywhere else. Multiply any matrix by I and nothing changes. It is the matrix version of the number 1. Now the definition. The inverse of a written A with a little -1 is the matrix that satisfies this. A times A inverse and A inverse times A both give the identity. It undoes A from either side. To ground rules. First, only square matrices, n by n, can have an inverse in this sense. You need the same identity on both sides. Second, some square matrices simply have no inverse. When the inverse exists, we call it invertible or non-singular. When it doesn't, we call a singular. Those two words come up constantly, so it's worth pinning them down now. For a 2 by 2 matrix, there is a clean formula you can carry in your head. Start with a general A, entries A, B, C, D. First compute one number, the determinant, a D minus BC. Keep that number close. It is about to sit under everything. And here is the recipe. Swap A and D. The diagonal entries trade places. Negate B and C. The off-diagonal ones flip sign. Then divide the whole thing by the determinant. Look where the determinant lies. Right in the denominator. That single fact is the hinge of this entire lesson. Hold that thought. So follow the logic. If the determinant is 0, that denominator is 0, and you would be dividing by nothing. The formula breaks. And it breaks for a deep reason, not a technical one. Remember, the determinant measures how area scales. When it is 0, the transform squashes the whole plane flat. The square gets crushed down onto a single line, all its area gone. And once space is flattened, there is no way back. Countless different starting points all landed on that same line, so nothing could ever untangle them. A singular matrix destroys information, and destroyed information cannot be undone. That is why no inverse exists. Let's put the formula to work on a real matrix. Here is a 4, 7, 2, 6. Step 1. The determinant. 4 times 6 is 24, 7 times 2 is 14, and the difference is 10, not 0. So A is invertible. Good. Step 2. Apply the recipe. Swap the 4 and the 6 onto the diagonal, negate the 7 and the 2, and divide by 10. That gives 0.6, minus 0.7, minus 0.2, 0.4. Never just trust it. Verify it. Multiply A by the inverse we found, and we should land on the identity. Exactly. Top lift? 4 times 0.6 plus 7 times minus 0.2. That's 2.4 minus 1.4, a clean one. Top right cancels to 0. Bottom left cancels to 0. Bottom right gives 1. Once on the diagonal, zeros off it. The identity exactly as promised. The inverse is correct. The 2 by 2 formula is lovely, but it does not scale. For a 3 by 3 or bigger, We need a general method, and the cleanest one is Gauss-Jordan elimination. The idea is beautifully simple. Write A and the identity side by side, one big augmented block. Then do row operations, the same moves you use to solve a system, until the left half becomes the identity. And here is the payoff. Whatever those same operations did to the right half, they turn the identity into an inverse. Drive the left side to I, and the inverse appears on the right, for free. Let's see it run. Here is our matrix A, and I've already stacked the identity on its right, with a bar between them. The left three columns are A, the right three start as the identity. Our whole job is to turn that left block into the identity. First, clear the entries below the top left one. Add row 1 to row 2, and the -1 under the pivot becomes 0. Notice the right side records the move. That row now reads 1, 1, 0. Now subtract row 1 from row 3 to kill the one in the bottom left. The left column is clean. Only the pivot survives. The right side keeps score, becoming -1, 0, 1. The third pivot sits at -1. So multiply the whole row by -1 to make it a proud positive 1. The right side flips to 1, 0, -1. Now sweep upward. Subtract row 3 from row 1 to knock out the one above the third pivot. Row 1's left half is now a perfect 1, 0, 1 entry left. The one above in row 2. Subtract row 3 once more, and it vanishes. Look at the left block now. It is the identity. Exactly. And there it is. The left side reached the identity. So by our rule, the right side is now A inverse. 0, 0, 1, 0, 1, 1, 1, 1, 0, -1. We raw reduced our way straight to the inverse. No formula needed. Sanity check one entry if you like. A stop row is 1, 0, 1 times the inverse's first column 0, 0, 1 gives 1. The top left of the identity. Every entry checks the same way. Now a cautionary example. A matrix that has no inverse at all. Here is S, 2, 4, 1, 2. It looks perfectly ordinary. Let's test it the only way that matters. Compute the determinant. 2 times 2 is 4. 4 times 1 is 4. And the difference is 0. The determinant vanishes, which means instantly S is singular. No inverse exists, and there is nothing more to compute. And you can see why in the numbers. The second row, 1, 2, is just half of the first, 2, 4. The rows point the same way. They carry no independent information. That is the fingerprint of a singular matrix, and exactly why it flattens space and cannot be reversed. Your turn. Here is a fresh matrix, C, 3, 5, 1, 2. Pause the video right now and find its inverse with the 2 by 2 formula. Compute the determinant first, then apply the recipe. I'll wait. Here's the walkthrough. The determinant is 3 times 2 minus 5 times 1, 6 minus 5, which is 1. A determinant of 1 is a gift. The division does nothing. Now the recipe. Swap the 3 and the 2, negate the 5 and the 1, and divide by 1. The inverse is 2, minus 5, minus 1, 3. If you landed there, you've genuinely got this. Trap 1. Reaching for the inverse of a non-square matrix. A 3 by 2, a 2 by 3. They can never satisfy a times b equals a square identity on both sides. If a matrix isn't square, the answer is simply no inverse exists. Trap 2. Forgetting the determinant. Writing d minus b minus c, a, and stopping there is a classic slip. Without dividing by the determinant, that matrix is not the inverse. It won't give you the identity. Never drop the 1 over AD minus BC. Trap 3. The inverse of a product. To undo a then B, you must undo B first, then A. So the inverse of AB is B inverse times A inverse. with the order flipped. Reversing it is not optional. The matrices generally don't commute. Let's lock it all in. The inverse is the matrix that undoes a times A inverse, and a inverse times A. Both give the identity. A matrix is invertible exactly when its determinant is non-zero. Zero determinant means space collapsed, and there is no way back. For a 2 by 2, swap the diagonal, negate the off-diagonal, and divide by the determinant, never forgetting that division. And for any size, augment with the identity and reduce until the left becomes I. The right hands you the inverse. Master these 4 lines, and the matrix inverse will never trip you up again.